Now that we know what our linear combinations of atomic orbitals look like for these molecular orbitals, let's think about how we might discern which one is the lowest energy and then which one is the next energy and the next energy and up to the highest energy. So the way that we're going to think about this is to think about the number of nodes in these wave functions. So if you think back to our particle in a box wave functions, the lowest energy wave function had no nodes. The next one had one node. The next one had two nodes, etc., etc. So 0 nodes, 1 nodes, 2 nodes. And we can see that the more nodes that the wave function has, the larger its wavelength, and therefore the lower its kinetic energy. And so in general, the more nodes that a wave function has means that it is higher in energy. So using that principle, we can think about our linear combinations of atomic orbitals. So here we have pictures of those like we drew before when we were thinking about how to combine these orbitals. And I've written out the linear combinations that these pictures correspond to. So this one is adding two s orbitals together on different nuclei. This is subtracting two s orbitals. Here we've subtracted two p sub z orbitals together to get this bonding orbital. And then here we've added two p sub x or two p sub y orbitals together. So there are two of these. They're oriented 90 degrees from each other. One we've added px orbitals, and one of them we've added py orbitals. And then we can subtract the px orbitals or subtract the py orbitals. That gives us this anti-bonding pi orbital. And then finally, we can add the two pz orbitals to get this anti-bonding sigma orbital from the p sub z orbitals. So if we look at the number of angular nodes in each of these wave functions, we can see that this sigma orbital made from, sigma bonding orbital made from the two s's has no nodes. There's no place where you change sign. So the colors represent the sign of the wave function. So let's say red is plus and blue is minus. So there's no place where we change the sign. So this has 0 nodes. And then if we look at this anti-bonding sigma orbital, we can see that there is an angular node here. There's also a radial node. If we walk out from the center, we go from blue to red, red to blue. So there is a radial node, but we're going to count angular nodes. So this has one angular node. And then if we look at the sigma bonding orbital that we make from the pz orbitals, we can see that there are 2 angular nodes in this one. And then if we look at the pi orbital, that the bonding orbital that's made from the px, adding px's or adding py's together, so again, there's 2 of these, we see that there's an angular node here. So there's 1 angular node here. And then in this pi anti-bonding orbital where we've subtracted px or subtracted py, we end up with 2 angular nodes. And then finally, in our wave function that is the anti-bonding sigma orbital that we get from the p sub z, we can find 1, 2, 3 angular nodes. So there are 3 of these. So this suggests that we should order the orbitals in terms of a sigma made from the 2s with 0 nodes, and then our sigma anti-bonding made from the 2s. That's going to be lower in energy than this pi orbital that has 1 node, because these are made from orbitals that are inherently lower in energy. They're s orbitals as opposed to the p orbitals, so they're inherently lower in energy. So these two, and we haven't allowed the p orbitals to mix with the s orbitals, and so these 2 s orbitals are the lowest in energy. Then if we look at this group of linear combinations where we've combined p orbitals for our next group, we will see that we should put the pi orbitals made from the 2px or y atomic orbitals, because that has one node, so that should be lower in energy than this one, or this one. And so then our next one should either be the pi antibonding or sigma bonding. And it turns out that the bonding is always lower in energy than the antibonding. And so this sigma bonding made from the pz orbitals is next. And then we have the antibonding that has two nodes. So that's going to be the next energy. So pi antibonding made from 2px or 2py. And then finally, the last one with three nodes would be the sigma antibonding that's made from the 2pz. So in general, this is the order of energies for our molecular orbitals. So if we look at the homonuclear diatomics that we can make from the second row elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, and we look at the actual order of these orbitals, we can see that, in fact, for all the elements up to nitrogen, the order that we predicted based on the number of nodes is correct. We go from sigma made from the 2s is the lowest, and then next is the sigma star made from the 2s. Then we have our 2 pi orbitals, then our sigma from the 2pz, our 2 pi antibonding, and the sigma from the 2pz. So this is exactly as predicted by looking at the number of nodes. Now, what we need to remember is that the 2s atomic orbitals have the right symmetry to mix in with the 2pz orbitals. And so if the 2s and the 2pz atomic orbitals are close enough in energy, then the 2s is going to mix into the 2pz. And when the 2s mixes into the 2pz, because 2s is lower in energy, and the energy of that mixed orbital is going to be the weighted average of the energies of the atomic orbitals, that ends up lowering the energy of this sigma 2pz orbital. So we can see that as we go across the periodic table, that 2pz orbital gets lower and lower and lower, which indicates that we're mixing in more and more of this 2s orbital into the 2pz. Notice that the antibonding does the same thing because we've mixed this 2s orbital into this to make the antibonding orbitals as well. And so because we get that lowering of the energy, eventually the sigma orbital from the 2pz gets lower in energy than the pi orbitals made from the 2px and the 2py. So that flips the order of these energies for the heavier elements. And the reason for that is because the more protons you get in the nucleus, the closer the energy of the 2s and the 2p orbital atomic orbitals are. So those energies also depend on the number of charges in the nucleus in terms of those atomic orbitals. And so for elements, diatomics that we make from oxygen and fluorine, we have to flip the order of the sigma 2p Z and the pi 2px and 2py.